1.3, classification of differential equations. So first, an ordinary differential equation, or ODE. So a lot of times we just say ODE. First, I'll give you an implicit ordinary differential equation of order n. So suppose I have a independent variable, x, and I have some function y of x. Then if there exists some function f of x, y prime, y double prime, way up to the nth derivative of y equaling 0, then we say that this is a ordinary differential equation. Ordinary because it involves ordinary derivatives. It is order n because it involves the nth derivative. It is implicit because you may not see here, you can't solve for the nth derivative in turn. You might not be able to solve for the nth derivative in terms of the other variables, variables and derivatives. An explicit ordinary differential equation of order n is, well, you are able to solve for the derivative of y. So if y, the nth derivative of y, so many times I'll use this Lagrange notation, this prime notation for derivatives. Okay, not always, but sometimes. I might also use the differential forms notation. And sometimes Leibniz notation. It just sort of depends. So an explicit ordinary differential equation of order n has the form: the nth derivative of y is equal to f x y prime all the way up to y to the n minus first derivative. So that those are ordinary differential equations. Okay. A partial differential equation of order n, I'll only say this like once, what a partial differential equation is, well, rather than having just one variable, independent variable, x, we may have several independent variables. Let's say x1, x2, all the way up to x sub m. And we have partial derivatives with respect to each of these variables up to the nth partial derivative. So I don't know, let's say the partial of u, I guess I'll call my dependent variable u respect to x1, partial of u respect to x2, all the way up to, well, the nth partial of u with respect to x sub m. Suppose that that's equal to 0. That is a partial differential equation. We will not, in this course, be looking at partial differential equations. Ordinary differential equations are difficult enough. This is an implicit partial differential equation. In general, partial differential equations are so difficult that it's hard enough solving explicit linear partial differential equations are just about, well, that's just about as far as most people have gotten. There are a few nonlinear, but it's basically partial differential equations, some first order linear partial differential equations certainly you can do. But those are much, much more difficult than differential equations. So first we have to get under our hat differential equations before we talk about partial equations. We will not do it in this class. You probably won't for several more years, probably at least 2 or 3 more years of doing stuff before you start talking about partial differential equations. So systems of ordinary differential equations. So if you have F1, F2, Fk, and so if there are a whole bunch of differential equations, then we say it's a system of ordinary differential equations. A linear ordinary differential equation of order n. Well, a sub n, the nth derivative of y, plus a sub n minus 1, the n minus first derivative of y, plus dot, 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 a sub 0 times, well, the 0th derivative of y, so just y, plus maybe b equals 0. So this is an example of a linear ordinary differential equation of order n. So a nth order linear ODE. An equation that is not linear is said to be nonlinear. There are many differential equations. I was going to start to list them, but I said, nah, they won't mean anything to you. So maybe I will list the first order named differential equation at the end of chapter 1. I think that's when we finish off first order. So I'll do that, not this section, but after you've gotten more experienced actually involving the techniques. So then I can also list techniques and other things. Oh, a solution. A solution to, say, some differential equation, say some nth order differential equation, f, x, y, y double prime, y triple prime, da da da, y to the nth power, equaling 0, on some closed interval. Let's do it on some open interval. On some open interval, alpha beta. Why did I pick alpha and beta? I don't know why. Is some function phi such that if you replace y by phi, then this equation is satisfied everywhere in that particular open interval. Okay, so let me do some examples. Let's say in each, oh, here it is. In each of problems 15 through 18, determine the values of R for which the given differential equation has solutions of the form e to the RT. So, oh, let me get rid of this. Let me get rid of the work. Okay, 1 second. There it is. Computer's just a little slow. Here it is. So, there are many, well, I guess I'll say this before I even at the beginning of the course. In differential equations, the way that I'm going to teach this course is it'll mostly be taught almost as a cookbook sort of fashion, where I give you techniques, you look at and classify a particular differential equation and use a technique, and you're able to solve it using that technique. In addition, I'll also give you a bag of tricks saying, okay, these tricks you can use to try to solve any sort of differential equation. I will also give you a little bit of reasoning and theory why these techniques work. Not too much theory, but a little bit to at least give you a hint of work the way they do. So at least to give them, put in context why we're doing these sorts of techniques. Okay, so first off for here, you just sort of say, well, let me guess that my solution has a particular form. And from that, let's see if I can find some solutions. And so, suppose that y equals e to the RT, then y prime equals r, y double prime. Well, e to the RT is just a derivative of that against another r. R is constant, so we don't care about that when taking the derivative. So this will just be r squared e to the RT. The third derivative, well, again, you're going to bring down another r. So it'll be an r times r squared is r cubed e to the RT. And so let's plug back in. So this equation becomes r cubed e to the RT minus 3 r squared e to the RT plus 2r e to the RT. And that's going to equal 0. Well, let's factor out r and e to the RT. What remains is r squared minus 3r plus 2. And let's factor out e to the RT. Well, I can factor out r squared minus 3r plus 2, r minus 2, r minus 1. Okay. Okay. R minus 2, r minus 1, e to the RT. This is equal to 0. Okay, so set each factor to 0 and solve for r. Well, e to the RT is not 0, so that doesn't give us anything. Well, so either r is 0 to both sides of your equation, r is equal to 2, or adding 1 to both sides of your equation, r is equal to 1. And so I have found all the values of r such that solutions of the form e to the RT, such that e to the RT is a solution to my particular differential equation. Okay. So that finishes off section 1.3. Any questions on section 1.3? So this is a quick classification of differential equations. I have not given you every classification for differential equations. There are many more classes, many more ways to classify differential equations. This will be done throughout the course.